Okay, so now let's just go back to those two examples we talked about in the beginning of the video and see what they look like. Let's see how they're different now that we have a protecting group in the mix. Okay, so in the first case, we wanted to utilize a molecule like this and turn it into a nucleophile, so make a Grignard out of that alkyl bromide. So let's say, for example, that we were targeting the synthesis of the following molecule. Okay, and so we want to use this molecule to make this molecule. Now, one of the steps that I'm going to talk about will be shown in the next video when I talk about the synthesis of alcohols. So you might watch that one in conjunction with this one. But if you just look, we got 1, 2, 3 carbons here. And in the product, we can see we've got 1, 2, 3, and then there's these extra 2 carbons, so 4 and 5. So somehow we need to bring in a 2-carbon piece. And the way that we'd like to do that is to convert this into a Grignard reagent and then react it with an electrophile that allows us to do that. But as we discussed, on this molecule, we're not able to form a Grignard directly because of the issue of deprotonation of that hydroxyl. But now that we have discussed how to protect that alcohol, this will be a lot more straightforward. So in the first step, we're just going to protect as the TMS ether. Okay, so TMS chloride and triethylamine will get us to this compound, so that's good. And now the silyl ether is stable to Grignard formation. So now we can go ahead, react that with our magnesium metal, and get to the following Grignard reagent. Okay. So there's our Grignard, and now this is perfectly acceptable. There's no more acidic protons, so we remove that issue. And so now we would generate this in situ, and then we're going to react that with an appropriate electrophile. And what we're going to do in this case is bring in those 2 extra carbons in the form of an aldehyde, specifically acetaldehyde. Okay, so that's going to be those 2 carbons. And so when we do that, we'll come down here. We will get to this molecule, and I'm going to put a proton there. So here we're going to do an acidic workup, and that's just going to quench our alkoxide that we would generate, which you'll see in the next video. Okay, so we get to this product, and you can see we're almost there. Now all we have to do is to deprotect, and so I can just use some aqueous acid, or it would be acceptable to use TBAF in this case. It's actually overkill. You don't need TBAF to deprotect a primary TMS group, but either one of these will work. And if we do that, then we can get to the target molecule. Okay, so that's how we can use a protecting group to, for example, use Grignard reagents. Okay, what about the second of our examples? Remember, this was a case where we were trying to think about selectivity in terms of oxidizing 1 of 2 alcohols. Okay, so here what we were trying to do is to think of a way that we could take the diol on the left and get it to this ketone selectively. Okay, but the problem is that again, if I just treat this with 1 equivalent of PCC, there's not enough of a selectivity between primary and secondary to expect there to be a good yield of this material. And in fact, I mean, if anything, you would expect the selectivity to be the other way, where the less hindered primary alcohol is probably going to react preferentially. So that's not going to give us good access to this compound. But what we can do is to use our protection to achieve that goal. And now this brings up a very good point in terms of silyl protection. So you can protect primary, secondary, tertiary alcohols. All of that is perfectly fine, acceptable. But there is a kinetic preference, as you probably expect. So the less hindered an alcohol, the more rapidly it will do that SN2 mechanism to be silated. So primary alcohols will be selectively silated first, followed by secondary, followed by tertiary. So what that means is that if we treat this with 1 equivalent of TMS chloride and triethylamine, we can expect a pretty darn good selectivity for silation of the primary alcohol over the secondary. So that now protects that primary alcohol, leaving the other one free to now do our PCC reaction. And now we don't have to worry about selectivity because we only have one free hydroxy group. Okay, and there's our oxidized secondary alcohol. And now the final step is to simply deprotect, remove the silicon group, and there we've got to our product. Okay, so those are two examples of how we can use silyl protection to do selective chemistry with alcohols.